submitting and monitoring jobs. So one of the key parts of submitting jobs to the scheduler is the Slurm batch script. So this is just a shell script. How familiar are we with shell scripts? Written them before, maybe? So about half of us. So scripting is a really useful way, just in general, of automating things. And it's just worth, sometimes when you're doing something, you're like, should I take the time to put this into a script so I can run the script again? It's just a bunch of commands that will rerun over when you run the script in a file. And I guess when I was introduced to it, when I was doing a radio astronomy PhD, the use case example was there was some, I think, observers doing follow-up observations where there was I think an event in optical, the optical astronomers would see, and then they would announce it, and then all the radio astronomers would then sort of point their telescopes to try and catch any ongoing phenomenon after the fact. And one of the students was there sort of typing in the commands to do all the data processing that was coming out of this thing one by one, and then by the time he was only like a quarter of the way through it, someone else had posted the results. It's like, how's that possible? The answer is that the other group had a script of those commands already typed in. They pressed a button and the computer went and did it. So an important thing is that you want to have scripted everything so that the computer's never waiting for you to type the command. So you don't want 1,000 nodes sitting there while you're sort of typing the command to run your program. You want it to, when you get the 1,000 nodes, it's going to hit your script and run straight away. And on top of that, it's very repeatable. Like if you go back a couple of months later and your bash history is gone and you're like, what did I do? You can look at the script and say, okay, there's all the commands that the script ran. So it's just good from that point of view as well. So that's, I guess, shell scripts in an introduction. So the Slurm uses those shell scripts to actually capture not just the work that it's going to run on your behalf. So like I said, it could be in the middle of the night that it runs. It's going to run the script of commands that you provided to it during the day. And on top of that, it also contains directives about what you're asking for. So the script kind of gets used twice. When you submit it, the scheduler is going to look at it and say, well, what do you need? And then when what you need is available, it will then use it again to then run the commands in the script on your behalf. And so these, in terms of what do you need, that's what these sbatch directives are. They're comments in the script. So when your script is run, they won't get executed because they're just comments. But when you submit your script to the scheduler is going to look into your script for those comments to try and figure out what it is you're asking for. And you can specify what you're asking for either in the script with these comment sbatch directives, or you could also do it at the command line. And you saw me do that with the dash dash account and dash dash reservation, where I was overriding what was in the script with additional options. And so our advice is to always have it in the script unless you're doing something that's sort of a once-off. So in that case, like it was a once-off, like the script does what it does, but in this case, I wanted to use this reservation. It's not really changing what the script's doing. Let's have a look at an example. We're going to be doing some stuff. I think I've talked about the reservation ID and we've looked at the SQ-me. Let's cancel. So yes, definitely. So if you've got, say, one account specified in the job script or the batch script, and then at the command line you override that, then what you type at the command line with the dash dash will override it. That's a good question. So let me switch across to the terminal and we'll actually have a look at it. And it's over here now for some reason. There we go. So I'm just going to go up a directory if you're wanting to follow along, and I'm going to go into the running jobs part of the examples. And if we have a look in there with an ls, you can see there's a submit_monitor.sh. So if I just look at that, I'll use the less program, submit_monitor.sh. You can see this is the contents of that script. And the first line is a line that you find at the top of any bash script. So by default, the shell environment on Sotonix is the bash shell, the born again shell. And so that first line, the hash exclamation mark is telling the operating system that this is a script that can be run by the interpreter found in /bin/bash. The -L is telling it to run the script as if you were logging in, so to process all your login scripts to set up the environment for running the script. And then we have these sbatch comments, and that is where we're asking the scheduler or telling the scheduler what we want. So in this example, we're setting up the name of the job to be submit_monitor. That's what it's going to show up as in the SQ output. We have the petition. We're going to submit this to the work petition. We have the number of tasks. That's the number of processes that we're going to run. This will become more relevant when we start to talk about parallel, launching parallel jobs later. Likewise, the number of tasks per node. If we have multi-node jobs, how do we want to distribute the processes across those nodes, and the CPUs or cores per task. And in this case, we're just going to run one thing, so it's just one for everything, and we're just going to run for 1 minute. And so so when the scheduler gets this, it's going to look in, see all that stuff we're asking for, and then it's going to put it into the queue and identify when we get to the highest priority in looking through, when there's a space that is one core for 1 minute, it's then going to take that time on that core and then run this script for us. And at that time, the script gets run on the node. All of the sbatches are comments, so they're just going to get ignored at that point. And then it's just going to execute line by line through the remainder of the script. So you can see here it's going to echo out the date. It's going to print the host name a few times with sleep in between, and then it's going to print the date again. Let's do that. So I'll just press Q to quit out of less and do an sbatch. In fact, I'm going to use my Control R to recursively search my history for the last time I typed sbat, and it's found the last time I typed it in because I don't want to have to retype the account and reservation. And then I'm going to come across and just change first job to submit monitor. .sh. That's submitted. You can see it as before with sq-me. Now it's running. So it's done those 2 steps quite quickly. Those 2 steps might not happen very close together. If it's a really big job, it might put it in the queue and it would still be pending. And then at some point later, it would actually run the script. If you have a look at when we did the sbatch up there, you can see shortly afterwards, there was a submitted batch job 187659119. So that's the job number that's going to show up in that SQ. And you can see it there, it's the same number, right? And if I wanted to cancel the job, if I decided something had gone horribly wrong, I was monitoring intermediate output on a really large job, it was going to cost me a lot of SU, I might choose to scancel. So you'd type it in, number 9. And then hopefully if I put it in time, it would have cancelled the job. And you see when I'm looking in the current directory that I'm in, there's this slurm dash and then the job ID dot out. So that's the output from that job. When the job's finished, it will put it out. It will only output that output when the job is finished. It will be sort of saving the output on all of the nodes and then at the end putting it out. The reason why it does this is to try and keep the interconnect clear of unnecessary communication. So if you are keen to find out the output of your job while it's going, you'll want to redirect the output of your program to a file, so it's getting written to the file system as it goes, rather than waiting for the fbash.out file to appear. So we can have a look at that. To be honest, I'm not sure what's going to be in it, given I cancelled it, but let's have a look. Looks like it must have more or less finished by the time I got there, because it's printed out the date and the two host names. If you are looking for errors, this .out file is the place to look. It will tell you things like your job ran out of time or being were cancelled for various reasons, run out of memory perhaps. But that's definitely worth always having a look at after you run a job. Where are we? So was everyone following along then, or do we want to have a go? We're good? Okay, we'll keep going. Feel free to have a go. I covered that. One thing you'll note in the when you run the hostname command, it's a really useful command to know because it'll print out the name of the node that you're running on. For example, when I was here at the login node, it will actually tell you in the prompt. You can see I'm C Harris at Sotonix02. I'm on login node number 2. But if I typed hostname, it'll also tell me that I'm on Sotonix02. So all of the login nodes will start with Sotonix and then a number. There's sort of half a dozen of them. Whereas here you can see the host name of the job had a NID and then a very big number. That's because all of the compute nodes have this NID naming convention. So you can see which nodes you're running on. And you might remember, you might have seen them before when we were looking at the output of sinfo. You can see these numbers here are referring to those NID numbers as to what state they're all in. So feel free to submit the time limit.sh and see how it goes. So this one, I think, has a 1 minute maximum wall time. But if you look at the actual contents of the job script, it actually runs for longer than a minute. So the idea of this exercise is, it answers the question, if I ask for particular time, like half an hour, and then my computational job runs for a couple of hours, what happens after half an hour? And the answer is that your job will get canned by the scheduler because other people have been scheduled to run after that. So then you have the following question of like, how long should I ask for if I'm not sure how long my job is going to run for? And the answer is, to start with, you just put in the maximum wall time, so 24 hours. After a while, you'll probably get a feel for how long your job's going to take to run. You might be like, well, I've run this workflow lots of times. It takes on average 8 to 10 hours. Maybe you put a wall time in of 12 hours to give a bit of leeway for how long it's going to run. Because you don't want to have the scheduler kill your job before it's finished and not get your results. So if your job is cancelled, you might be able to see yourself if you're doing the example and look in the output file. You'll see it's cancelled due to time limit. Other things you might see, if you are coding in a memory unsafe programming language, you might get a segfault. There's ways of going about debugging that with a debugger. If you hit those, feel free to open a help desk ticket and we're happy to show you how. And then another possibility is you ran out of memory. So say you, as Christian was saying, you could ask for half the memory on a node. What happens if your program suddenly starts using 3/4 of the memory? The schedule is going to pick up on that and say, hey, you've used more than you said you were going to, you're getting shut off because the other jobs running on that system might need that memory. So the general rule of thumb is ask for slightly more than you think you're going to need and get to know your workflow. The most important thing is if something's gone wrong and you're not sure what, always check that output file and look for messages that are error messages. So things that have error is usually the important line that you want to be looking for. And if you're opening up a help desk ticket, you want to kind of provide the job ID and like a copy paste of the error message, because that's going to really accelerate how quickly we can help you identify the issue. So that's a good thing to provide. So how do we find out about more information about the jobs that are queued and jobs that we've run? So S-control show job, and then where it says job ID, you put in the job number that we saw earlier. That will tell you a bunch about jobs that are currently in the queue. If you can't remember what you've asked for, that's a way of querying it. Once your job has run, it shows up in S-account. And so S-account can be used to search for all the jobs that will run in a specific time frame. And there's lots of command line options that you can use to sort of narrow down the types of jobs you're wanting to. So like, what are all the jobs that I ran last Monday in the debug queue, for example? I'll sort of find out that information with this account. There's also SF, which is short for Slurm efficiency, which provides some information about the resource usage of your job, if you're interested in how efficient it is. So that can be useful as well. But note that Ceph assumes you're using the hyperthreading for CPU efficiency, so it might be out by a factor of 2. So if you just type in S-account, this is the kind of thing you might see. I might just switch across to the prompt. So S-account. And you can see here's all the jobs I've been running. You'll note that there's actually 3 entries for each job, and that's to do with the actual sort of job you've submitted, the batch script execution that you have, and then any job steps that you have within that with srun, which I haven't talked about yet, but we'll get there. Useful things to see here, in particular, are the allocated CPUs to know how big your job was, and the completed state. So all these jobs finish successfully. If for some reason something gets killed or you have an error in your code and your code actually returns an error code, Slurm will capture that and print it there so you can see which jobs have failed. So another thing you can do in addition to submitting Slurm batch scripts is to have an interactive session where you can actually type the commands in. So the select is the command you use to do this, and select takes the same options as sbatch, except because there's no bash script, you can't put the sbash directives in the batch script. It all has to be on the command line. So you can use these interactive sessions for debugging, compiling. Usually you grab a node in the debug queue or the GPU dev queue, for example. If you just type salloc, I think it'll give you by default an hour for one core in the work queue. And then if you start specifying things, it'll start overriding those defaults. So let's have a go. So if I just, again, recursively search for that SBatch, Control R, I'm doing that because I want to capture these -- account and reservations, but I'm going to replace my SBatch with an salloc. And then I'll just take the job script off the end because we don't need that anymore. And I'm just going to do a -n1 because I want one process. So that's given an allocation and waiting for resource configuration. Sometimes, so this is because we're in a reservation, there's a node there ready. If you have to wait, you might find it says that it's sort of sitting in queue. Then you have to maybe wait for a node to become available before it drops through to the node. But you can see here I'm now interactively on node 1002 by post name. And so this is really good if you are trying to figure out what's going on with your job script, because you can put all of the SBatch commands in at the command line and drop in and then start copy pasting your job script line by line and then be able to query things. So it's really useful for debugging. One thing to bear in mind is that while it's sitting here at that prompt, node 1002 is not doing anything, but it's being occupied. So you don't want to do this with multiple nodes and then go away to lunch leaving it here, because other people can't use that node, other work can't get run on that node. So this is only for sort of actively, interactively trying to fix things. And ultimately you want to be submitting 99% of your work using SBatch. This is for ease of use of figuring out what's going wrong with your SBatched batch scripts. To get out, we can do Control D or type exit, and that just brings us back out to the login node. So to go into a little bit more detail on the actual writing of batch scripts I'm going to use, we're going to start off by taking a quick aside into parallel programming. Who here has done sort of parallel programming before? About half, okay. So in order to use the supercomputer is just a bunch of computers, thousands of them with many cores. And if you just take a normal program that's just written serially to execute instructions one after the other, like most programs are, it's only going to run on one core. So you're only going to be able to use a teeny tiny little fraction of the supercomputer. And chances are, because there's so many cores on the supercomputer, they're actually clock slower for power efficiency. So you might take your serial program that you wrote on your laptop, put it on the supercomputer, and find out it's actually running slower. The way that you actually take advantage of the processing power of the supercomputer is you have to have parallelism in your program. And what that looks like is having multiple threads of execution all working at the same time on the same problem, or multiple instances of your program all running together on different parts of the problem and talking to each other. And so in order to, I guess, talk about that and how you're making use of the supercomputer, it's important to have a few terms that you're aware of. So one is a process. When you are running a program, the instance of that program that is running, we call a process. And a process has access to all of the variables in the program, but it can't see the variables of other processes or other programs that are running on the system. We also have this concept of a thread. And so inside a process, you can have multiple threads of execution where there's multiple parts of the program running at the same time. And because they're inside the program, they can see the variables of the program. And so there's these kind of two types of parallelism. There's parallelism where you have one process with multiple threads of execution that can all share the variables. And there's a parallelism where you have multiple processes or multiple instances of your program that are all running, and they can't share variables directly. Like you can't just go look at what the value of X is. But there are library calls that you can make to communicate between them. So you have these communication layers for communicating between those processes. So we'll go into a little bit more detail. So the one where you have multiple processes that are communicating, this is called distributed memory parallelism. And so you can't see the variables of the other processes, so you have to communicate with it and say, hey, can you give me this data or information? And if you're using this kind of parallelism, the most common specification is MPI, the message passing interface. And this is what you want to use for your parallelization, because every supercomputer in the world supports MPI. It's also supported on your laptops, on multi-core. And so it's an industry standard that, and there's lots of optimized implementations for specific supercomputing infrastructure. That means it's really efficient. So if you're thinking about doing distributed memory parallelism, you want to be doing it with MPI. In contrast, there's shared memory parallelism, where you have lots of threads of execution. There's a number of different ways of doing this depending on the programming language. If you're using a traditional compiled language like Fortran, C or C++, then OpenMP is, again, a widely adopted standard that has a lot of effort and work going into it. It's what we recommend using for that particular type of parallelism. What's the main difference between them? If the main difference is that sharing of variables. In order for a variable to be shared between those threads of execution, it has to be visible in the memory. And so if you have multiple nodes or multiple computers, they have their own memory. And so the only way to scale across multiple nodes is to have separate programs or processes that are running on those nodes and using the distributed memory parallelism. You can't do the shared memory because it's different memory, it's different variables. And so often the threading or the shared memory parallelism is easier to implement because you can just have all your processes looking at each other's variables. But you're stuck on one node. And as we saw, there's 1,000 nodes there and you're only able to use one of them. So the distributed memory parallelism is more heavyweight. It requires more thinking because you've got to go, okay, I've got 1,000 instances of my program running. Each one's going to do its own bit of the problem, and it has to talk to all the other ones to figure out how to communicate and work that along. But it does mean you can scale across the whole machine, which is really cool. So just to further complicate things, there's also GPU accelerated parallelism. And so I think we've talked about CPUs and GPUs a lot today. Who knows what a GPU is? A few of us. So back last century, when computers were being developed, most computers had the central processing unit, the processor in it, that did all the processing. And what was happening is that a lot of the time of that processing was being taken up deciding what color the screen had to be. Because you've got all the pixels on the screen and that needs to be refreshed 60 times a second or more on some systems. And so they decided that it was more power efficient and better to offload that into a different type of processor called a graphics processing unit, to basically just figure out, based on what the CPU was doing, what all the pixels needed to be, what color they need to be. And probably around the beginning of this century through to about 2008, there was a big drive from computer-aided design as well as the consumer gaming industry, computer games, to try and get these photorealistic graphics, and these GPUs became really computationally capable. And around 2008, they were so sophisticated they could start running not just graphics applications, but just arbitrary code. And at that point, they realized that you could start using them for scientific applications, because it turns out that trying to figure out what color all the pixels should be 60 times a second is not that different from, say, doing a weather modeling code where you need to figure out the variables of a bunch of cells in a mesh very quickly. And so there's certain types of algorithms that the GPUs are actually really a power efficient way of doing that. And so we also have, in addition to the parallelism we saw on the last slide, these GPU programming APIs that offload work from the CPU to the GPU to do really power efficient computation. And so you can see some different interfaces there. We typically use HIP or OpenMP also supports target offloading. And what you'll find is that modern scientific programs that have been written for performance will often have a combination of all of these. So you might have MPI to allow you to run on multiple nodes, OpenMP for threading, and then OpenMP or HIP or CUDA to do the GPU offloading to the GPU. So it's just using all of these technologies together to run something at scale in a very performant, power efficient manner. So with that aside, we've got processors and threads and GPUs. Let's have a look at how we go about distributing work onto Photonics. So as I mentioned, all the bash scripts start with this first line. We then have all of the work that we want the script to do once it runs. Usually this will typically start off with some commands to configure the environment. So you might have some module loads to load up the software that you're going to be using. You might set some environment variables, do any preparatory work before then actually running your work. I think I've already talked through the SBatch directives. But now we can talk a little bit more about the tasks per node and CPUs per task that I kind of glossed over earlier. So the n tasks is the total number of parallel processes. The task per node is the number of processes per node. And then the CPUs per task is how many threads per process. And so this will vary depending on whether you've got MPI or OpenMP to do those different types of threading. As we'll see, we'll work through some examples shortly. Another thing you can do is share the nodes. If you do, there's some additional directives we recommend using, such as -- distribution block. This is just to make sure that when your work's being distributed onto those nodes, it's all being packed together, so it's going to run efficiently. And so it's really important if you start to write your own shell script, you go to the documentation and copy one of the examples that we've provided, because it will contain all of this sort of details in there, and then just start modifying it as you need for your particular workflow. If you want to have the entire node to yourself, there is this -- exclusive. So that's something you typically do if you sort of were packing the node full of compute or using multiple nodes. And that way you know that there's no one else on the node that's going to be using some of your memory bandwidth or eating up some of your time. So we definitely recommend always specifying everything, because defaults can change over time. Defaults might change from one system to another. So if you specify what it's doing, it's going to be consistent, and when you look back, you're going to know what was done. And it's always important to do a test run. Don't write your 1 million SU batch script and send it off, right? Because you might burn 1 million SU and not get what you thought you were getting. So do a lot of testing to make sure that you're getting what you think you're asking for, and then launch your larger job. So within the node, we've kind of done our example, but our example was only running on one core. How do we launch our parallel job out across multiple nodes or across multiple cores on a node? And the answer is you use srun. So every batch script, unless it's sort of a simple example, should have an srun command towards the end of it. And this is where you actually launch your program. It should automatically capture your what you specified with your processes through end tasks and your end tasks per node. We do recommend using the -c to specify the threads per process. I actually would personally recommend specifying -n and -N to specify the total, -N for the total number of processes, total number of processes per node, -N for the total number of processes, and -C for the number of cores per process, because I don't trust Slurm. Occasionally it's broken and that hasn't automatically sort of inherited. It may seem a little weird because we're specifying things twice here. Like we just told the scheduler in the beginning that what we wanted, why are we specifying it again when we're launching our job? And that's because we might have a more sophisticated workflow that's doing something like using all of the resources for most of the time, and then doing a little intermediate step that only requires a few cores before then going and using everything again. So there might be multiple sruns that aren't necessarily using all of the resources. And so that's why you've kind of got this two-step process there. So let's look at some examples. So this is an example for MPI with exclusive access and there's 2 nodes in this job script. The diagram is only showing one of the 2 nodes because they're identical. So if you think back, MPI was the one that had lots of processes that communicate with messaging. And so a process is represented by a P. And if you think back to what Christian was talking about earlier in terms of the processor architecture, what you're seeing here in the dark blue is one node, and then you've got 2 sockets or 2 physical processors on that node, which you've got there. The purple is the cache, the cyan blue, the light blue is the actual cores. So you can see you've got 2 lots of 64 for 128 total cores. And our job script is asking for 256 processes with 128 per node. So, and 1 core per process. So what it's going to do is it's going to go and put 1 process on every core of the of both of the 2 nodes. So this is what you might want to do if you had an MPI code, for example. So this is the other example where you had shared memory programming. So maybe you've got an OpenMP code. That means you can't run on multiple nodes because it needs to share variables, or has to be on the same node. So here we've got our primary process that is running on the first core. And then there's 128 threads that are running on each of the cores. And so all the threads here can actually see the variables of the process and talk to each other through variables. And you can see in asking for this, there's only one process, there's only one process per node, but there's 128 cores per process. So there's one for each thread. And there's OpenMP environment variables for defining how to sort of set the order of those. We have a hybrid approach. So here we have, again, 2 nodes. So there's two of those, there's only one shown. And here we've got 4 processes each with 64 threads. So within one processor, all of the threads are going to be communicating via variables. And then when you need to share information between processes, you then use MPI to talk between them. We could do shared access. We only need half a node. So we're only going to ask for 64 processes. Here we specify task per socket to try and make sure they're all on the same processor. And so again, you can see why, I guess, copying the templates and trying to find the right template to match what you're asking for can be useful. This is what happens when you have one serial program that just uses a lot of memory. So we're asking here for one process per node, one core per process, but we're asking for a lot of memory, dash memory. We're asking for 57 gigs. And so that's going to block out all of those cores because we can't use them because we're using the memory that's associated with them. And so that one thread has access to all of that memory and is going to use a quarter of the node. The GPUs, we need to use a dash GPU on the end of our project ID. So you can see that dash account. Normally for the CPUs, it would just be a project ID. You have a separate allocation for GPUs, so you need to put a dash GPU on the end of it. We're specifying the GPU partition, and that red box has shifted. It should be around the GRES GPU1. So this is saying I would like one GPU to make use of in this instance. On the GPU nodes, there's a pre-processing script that actually specifies the cores for you. So you don't actually specify. In fact, you get an error message if you try to specify the cores because you've asked for one GPU. There's 8 cores per GPU, so it will automatically allocate 8 cores for you. So have a go running a parallel job. So if you look in the running jobs examples, you should find a hello.c and a makefile. And if you run the command make, it should build it into an executable, hello.x. And then you could try running it with one of the job scripts there and have a look at the output. Yes. Yeah, there's 8.
Oh, yep. So is those SBAT scripts the only way to interact with multiple nodes? So like, for example, I'm thinking of something like PyTorch, where I know they have some like interface for like distributed memory parallelism. Is that restricted to that one like node when you try and use something like that? Or is there any like...
If you don't use srun, all of the threads will just get pinned to one process, one core. So you could ask for lots of stuff, but it'll just like put it on that one processor because you need to use srun to actually distribute it because it's pinning your processes and threads to the cores.
Okay. Yeah. Okay.
So you want to basically do an srun PyTorch.
And do multiple. Yeah. Okay.
Yeah.
All right. Thank you.
How are we going? Hands up if you've run the job. Okay, I'll walk us through it. So I'm going to city back into running jobs. No, examples. I can city into examples. Okay. I'll then type make. So that's compiled up the C code into a binary for running. Search again. Job hybrid BI. Goes. Right. So where did the output file end up? Yeah, why is it called something different? Yeah, that's right. So when we have a look at the script, which I've lost already, where is it? Job hybrid, thank you. You can see there it set the output equals %x dot out. Assuming %x is the name of the job script. I'm sure if you look at the manual pages for SBatch, there'll be a bunch of other stuff you could use there. All right. Having a quick look at the contents of that. No, not out. You can see we've got lots of different threads all writing out which process they were running on and which thread they were running on. So you can see there were the 64 threads. Some were processor rank 1. On my mouse, I can come up here far enough. Hopefully we'll see rank 0 or 4, rank 3 or 4, and different threads within that. So this, we're using MPI and OpenMP to run all this simultaneously, and then the output just sort of comes out in whatever particular order that happens to get combined together at the end. And so one of the things about using a supercomputer is, depending on the work that you're doing, there's a lot of areas where the parallel code has already been developed for you. So you don't really need to know how to program MPI or how to program OpenMP, but you do need to know how to launch them, right? So what you've done today in terms of running this script, that's enough for you to use an MPI enabled or an OpenMP enabled code and run it on the supercomputer. So hopefully that's helpful. Let's get back to the slides. I'm mindful we're getting towards the end of time. So we'll keep going on to the final module that I have for you, which is